Okay, think about it. The phone in your pocket, the electric car you might drive, heck, the entire power grid. Our modern world absolutely runs on batteries. But what if the tech we all rely on is kind of hitting a wall? Well, today we are diving into some absolutely mind-blowing research that points to a revolution. And get this, it's powered by something you probably have in your kitchen cabinet right now.
I mean, just let that sink in for a second. What if your battery was cheaper, safer, and made from one of the most common superabundant elements on the entire planet? That's the huge promise we're digging into today, and it all boils down to one simple but massive change.
All right, here's how we're going to break it down. First, we'll look at the battery dilemma. You know, the problem we're up against. Then, we'll dive into this incredible quantum search for a solution. After that, it's time for a materials showdown. And finally, we'll meet our champion anode.
All right, first up, the battery dilemma. So, why do we even need a change? I mean, aren't today's batteries pretty good? Well, yeah, but the tech that powers our world is starting to face some serious headwinds. Look, lithium-ion batteries have been a total game changer, no doubt about it. But here's the thing, they rely on lithium, and lithium is a limited resource. It's getting more and more expensive, and honestly, there are some big questions about its long-term sustainability. And as our hunger for energy just keeps growing, these problems, they're only going to get worse. And this is where the alternative comes in. Say hello to the sodium-ion battery. Yeah, sodium, as in table salt. It's one of the most abundant elements on Earth. So you're going from something scarce and pricey to something that's everywhere and super cheap. That shift alone is a massive game changer. But, of course, there's always a catch, right?
And the catch is this, a battery is only as good as its parts. To really unlock the full power of sodium-ion tech, scientists have to find the absolute perfect material for the anode. That's the part that grabs and holds on to the sodium ions when you're charging the battery. It's the key to the whole puzzle.
So how in the world do you find this perfect material without spending like decades in a lab just mixing and matching stuff? Well, you don't. You go quantum. You build a virtual laboratory to peek at how the atoms themselves are going to behave.
The tool for the job is called density functional theory, or DFT for short. Now, the best way to think about it is like a virtual microscope on steroids. It uses the fundamental rules of quantum mechanics to simulate and predict exactly how a material is going to act, before anyone even thinks about making it in the real world. It's pretty amazing.
So here's how this virtual lab process actually works. Researchers like Shivani V, who led this incredible study, they pick some promising candidate materials. Then, they throw them into this virtual gauntlet. They use DFT to check for stability, they simulate how well they conduct electricity, and this is the big one, they analyze how well they can store sodium. It's just a ridiculously efficient way to innovate.
And this whole process led to a showdown. 4 really promising, super thin, two-dimensional materials were picked to basically compete for the title of the best sodium-ion anode. Let the games begin.
And here are our contenders. On one side, we have the nitrides, compounds with nitrogen. On the other, the sulfides, compounds with sulfur. Each one of these was put through the DFT simulation ringer to see how it would stack up.
Okay, so the main event, the big test, it all came down to something called the diffusion barrier. Now, just think of it like an energy hill that the ions have to climb to move through the material. A smaller hill, a lower barrier, means the ions can just zoom through. And what does that mean for you? Faster charging. So for a battery, lower is always better.
And whoa, the results are just staggering. Seriously, look at this chart. The first material, g-C₃N₄, has a barrier of 0.28 electron volts. Not terrible. The next one, MoS₂, drops way down to a tiny 0.02. But then you look at WS₂. Its barrier is just 0.006 electron volts. I mean, that's not even a competition. That is like going from a 20-mile-per-hour school zone straight onto the German Autobahn with no speed limit.
But wait, there's more. The simulation found a hidden superpower. Check this out. When some of these materials soak up the sodium ions, they literally transform. They go from being semiconductors, which are kind of picky about conducting electricity, into full-blown metals. And this is a huge deal because it massively boosts their conductivity, which is exactly what you want for a super high-performance battery.
So, after that absolutely decisive showdown, I think it's pretty clear it is time to announce our winner. One material just stood head and shoulders above the rest.
And the champion is WS₂, or tungsten disulfide. It basically combined all the best qualities into one incredible knockout package.
So let's break down why it won so decisively. First, it had that amazing trick where it becomes metallic, giving it excellent conductivity. Second, it had that mind-blowingly low diffusion barrier for super-fast ion transport. And on top of all that, the simulations showed it could hold a ton of energy.
And here's the number to back that up, a theoretical capacity of 540 milliampere hours per gram. Now, to put that in perspective for you, that is a really, really competitive number for energy density. It suggests these batteries could hold a whole lot of charge for their weight.
And let's just come back to that unbelievable diffusion barrier one more time. 0.006 electron volts. Remember, lower is better, and this number is so low it's practically on the floor. This is the secret sauce, the magic ingredient that could give us ultra-fast charging sodium-ion batteries down the road.
You know, the lead researcher, Shivani V, she really hit the nail on the head. She said the combination of these properties makes tungsten disulfide a highly promising anode material for the next generation of batteries. And this isn't just a guess, it's backed up by some seriously powerful quantum simulations.
But really, the biggest takeaway here is even bigger than just this one material. What this research really gives us is a roadmap. It shows us how we can use these incredibly powerful computational tools, like DFT, to design and test the advanced energy materials of the future. We can accelerate discovery in a way that just wasn't possible before.
Which of course brings us to the final big question. Now look, there's still a long road from a simulation inside a computer to a physical battery in your phone or your car. But this research, it's a huge signpost pointing the way forward. And it really makes you wonder, doesn't it? How long until a discovery just like this one, born inside a supercomputer, is actually powering your world?